Newton's second law is just the relationship between force, mass, and acceleration. It's always seen as an equation. And the equation might look a little scary, but it's just saying that the acceleration is equal to this sigma here stands for the sum, add up all the forces. So the acceleration is equal to the sum of all the forces divided by the mass of the object the force is applied to. A couple things about that. Little arrows over the top of these letters indicate that these quantities are vectors. That force has both magnitude and direction, so does acceleration. And then we have metric units for this. So F stands for force, M stands for mass, A stands for acceleration, and the units of force would be newtons, mass is measured in kilograms, and acceleration is meters per second squared. We could do them in imperial units, and we would measure the force in pounds. And can you think of what the imperial unit of mass is? Well, it's actually slugs, and you may not have guessed that. And if we're measuring the acceleration in the metric system in meters per second squared, we would measure the acceleration in feet per second squared in the imperial system. And the imperial system is a little funny because we use the unit of pounds for force, and sometimes we use the unit of pounds for mass. So we say lbf, that's pounds of force, or lbm, pounds of mass. And I kind of prefer the metric system. So if I had a 1 kilogram mass and I put a little bit of force on it, a small amount of force, it's going to produce a small amount of acceleration. But if I had that same 1 kilogram mass and I put a big force on it, well, of course, it's going to produce a big acceleration. But if I put some amount of force, not saying how much force I'm going to put on that, but if some amount of force causes that 1 kilogram mass to accelerate at 1 meter per second squared, we're going to call that amount of force 1 Newton. And that's the very definition of what a Newton is. It's the amount of force that would accelerate 1 kilogram of mass at a rate of 1 meter per second squared. So we see Newton's second law here. Acceleration is the sum of the forces divided by the mass. And again, it's the 1 Newton of force would accelerate 1 kilogram of mass at a rate of 1 meter per second squared. And a lot of times we rearrange this equation and solve for the force. So force is equal to mass times acceleration. So if the units of force should be measured in newtons, and that is called the common unit. A common unit is just one word. The fundamental units, or the MKS units, also known as SI, Systems International, these are the fundamental units of acceleration, and this is the common unit of acceleration. So let's think about gravity now. If I had F sub g, anytime you have a subscript here, it's indicating which force we're talking about. So F sub g would be the force of gravity. So 1 kilogram of mass, how much force is on it? Well, we know that gravity is going to accelerate it at 9.8 meters per second squared. The definition of 1 Newton, 3 little lines here means definition, it's the amount of force needed to accelerate 1 kilogram of mass at a rate of 1 meter per second squared. So how much force would accelerate it 9.8 times as fast? Well, the force of gravity must have been 9.8 newtons. We say 1 kilogram weighs 9.8 newtons. This is mass, and this is weight. So I guess I didn't show you this before. We showed you this piece of Newton's second law, but that's also just another way of saying it, is the net force divided by the mass. So if we rearrange that and solve for the net force equals mass times acceleration. Or if we're talking about not just any old force, like pushing on a car or something, but gravity pulling on something, the force of gravity is mass, not times any old acceleration, but specifically the acceleration of gravity. Another way of saying the force of gravity is the weight of something. Notice that the weight, or maybe I should say here, notice that the force of gravity is not the same thing as the acceleration of gravity. Gravity is going to accelerate everything at 9.8 meters per second squared, but gravity does not put the same force on everything. The force of gravity depends on how much mass it has and the acceleration. So if I had a big mass here, 20.4 kilograms, in imperial units it weighs 45 pounds, but we could just take that mass of 20.4 kilograms, multiply by 9.8 meters per second squared, and we would get about 200 newtons. All right, so what we're going to do is we're going to do way more than just plug numbers into this. We're going to, at the end of this video, we're going to plug numbers into it and see how to use this equation. But more importantly for now is we want to identify 4 unique implications of Newton's second law of motion. We want to take this equation and tease out of it 4 big ideas. All right, so the first big idea is if we keep the force on an object constant, we don't vary that. Let's look at the relationship between mass and acceleration. Between acceleration and mass. We say that the acceleration is proportional to 1 over the mass. That means when the mass gets bigger, the acceleration gets smaller. Can you explain why that's true in one word? And that word would be inertia. The more mass an object has, the more inertia it has, the more it resists acceleration. So it'd have a smaller acceleration. Another piece of this is if we keep the mass constant. We don't change the mass of the object. That's going to put force and acceleration directly proportional to each other. So when the force goes up, so does the acceleration. And that one's not too surprising. You push on it harder, it's going to accelerate more. All right, the third thing we want to look at is acceleration will equal 0 if and only if the net force is 0. Now let me explain what I mean by this if and only if. This is an if-then statement that goes both ways. You could say if the acceleration equals 0, then the net force would equal 0. And the opposite would be true as well, that if the net force is 0, then the acceleration is 0. If the if-then statement can go both ways, you say if and only if. And that just means if this term is 0, this term is also going to be 0. And the last thing has to do with the fact that these are vector quantities. Acceleration has magnitude and direction. Force has magnitude and direction. So the acceleration, it will always be in the same direction as the net force. You put a net force on it to the right, it's going to accelerate to the right. So let's come back to this one. I'm going to look at some examples where acceleration and mass are inversely proportional.
1 minute 39 seconds into the flight, the Delta vehicle now only weighs about 1/2 of what it did at launch, expelling propellant now at the rate of about 2,700 pounds per second.
So when the rocket is expelling fuel out the back of it, the mass of that rocket is getting less and less and less. If the mass got to be half as much, and we applied the same amount of force, the acceleration would get twice as much. If mass got half as much, acceleration got twice as much. That's inverse relationship there. So we say a force is applied to a 2 kilogram mass, producing an acceleration of 10 meters per second squared. Okay. So now we're going to apply the same amount of force, but this time instead of 2 kilograms of mass, we're going to apply it to 4 kilograms of mass. Just get an idea of the proportionality here. the mass got twice as much, so the acceleration would get half as much. Remember, these are inversely proportional. More mass, more inertia, more resistance to acceleration. So if it resisted acceleration twice as much as here, it should have half as much acceleration. The same amount of force to 1 kilogram of mass. So the mass dropped from 2 to 1. The mass got to be half as much. The acceleration would be twice as much. And then here the mass became 10 times as much. The acceleration would be 1/10 as much. So 1/10 of that. And here the mass became 4 times as big. So the acceleration would be 1/4 as much. 1/4 of what that was. So that divided by 4 is 2.5 meters per second squared. All right, let's just another example of that. Let's say we have a motorcycle that has a mass of 100 kilograms and we put some force on it and it produces an acceleration pretty close to gravity. Now I'm saying I'm going to put the same amount of force on this motorcycle, on this race car, and it has 10 times as much mass. Now what I mean by the same amount of force is maybe we take the engine out of that and of the motorcycle and put it into the car. That'd be a crying shame, but it's an example. So because the mass got 10 times as much, the acceleration became 1/10 as much. Now we're going to put the same amount of force on this big truck here, and it has 5 times as much mass as this one, so it should have 1/5 the acceleration. So 1/5 of that is 0.2. All right, a couple examples showing how mass and acceleration are inversely proportional. That's the symbol for proportional. Now let's scoot over here and just an example or two looking at how force and acceleration are directly proportional. So if a force of 5 newtons produces an acceleration of 10 meters per second squared, a force of 10 newtons, twice as much, would produce twice the acceleration. This is kind of an easy one. If this aircraft normally accelerates at 2 meters per second squared and one of the 4 engines fails, goes kaboom, so only 3 out of the 4 engines are now going, that's 3/4 as much force, 3/4 as much acceleration. And that's probably all the examples I need to do on that one. Let's look at this one. The acceleration is 0 if and only if the net force is 0. So this person is pushing with 50 pounds of force on this refrigerator and moving it across the floor at 2 miles per hour. What is the net force on the refrigerator? Well, students are tempted to multiply those two numbers, or maybe they're tempted to divide those two numbers. Well, the question is, what's the net force on the refrigerator? And the answer is 0. It was going at a constant velocity. It was not accelerating. So the net force had to be 0. If the person was pushing to the right with 50 pounds of force, there must have been something pushing back to the left with 50 pounds of force. And that'd be friction between these two surfaces. Friction is something we're going to spend a lot of time on in an upcoming video. So here we have a rocket accelerating through space. A rocket is being accelerated by a force through space when suddenly it encounters a force, an equal amount of force in the opposite direction. The ship will be brought to a rapid halt, slowly come to a stop, or continue at the same speed it had just before the force began. Well, let's think about this. If it encounters an equal force in the opposite direction, what's the net force? Well, that would be 0. So a rapid halt is a big acceleration. But if the net force is 0, the acceleration would be 0. Slowly come to a stop, well, that's a small acceleration, but it's an acceleration. But if it continues at the same speed it had just before the force began, going the same speed in the same direction, is no acceleration. So no net force, no acceleration. So this is like putting an engine in the opposite direction on it, like this. We'll show it here. So we put a speedometer on this, and this thing's accelerating, going faster and faster and faster and faster, And when it gets to 40 meters per second, that engine came on. Now the forces are equal and opposite. The net force is 0. It didn't accelerate anymore. Okay, don't forget that one. That's kind of an important one. Net force is 0. The acceleration will also be 0. Now let's scoot over here and look at the last of the 4 things we need to remember, that the acceleration is in the same direction as the net force. So if you have a car and you press the gas, it's going to cause the car to accelerate to the right. The force was to the right, so the acceleration was also to the right. The acceleration will be in the same direction as the force. And if you hit the brakes, the brake puts a force back to the left, so the acceleration would also be back to the left. And we talked about this when we talked about simple kinematics, but the car could be moving to the right, but accelerating to the left. If it's moving to the right and accelerating to the left, it's slowing down. Anytime the velocity and the acceleration are in the same direction, you're going faster. When the velocity and the acceleration are in opposite directions, you're going slower. But no matter how you cut it, the force and the acceleration will always be in the same direction. So if you kick a soccer ball, once it leaves your foot, the only force acting on it is gravity, and gravity's pulling down the entire time, so it is accelerating down the entire time. Even when it's moving up, it's accelerating down because it's slowing down. I do like to poke fun of Hollywood. There's lots of material there for us to look at. So let's look at this one from Mission Impossible.
Ethan, get out of the truck! Ethan, move!
So how many of you saw this movie and said, wait a second, the acceleration was not in the same direction as the net force? Exploding bomb coming straight at the camera, the force is straight at the camera, and he accelerated off of that way. I don't get it. That is not entertaining, that is just insulting. So hopefully you don't appreciate being insulted. All right, here's a couple of examples where we are going to plug numbers into this equation, but we have to be careful. In middle school, you may have just plugged in an acceleration and the mass, and you had to find the force. But we're doing more than we did in middle school. So we have this cart. It's on wheels that are very, very low friction, a pulley here with very, very little friction, and we're going to hang 200 grams off the end of this. And the cart has a mass of 700 grams. We would like to figure out how fast it's going to accelerate. I guess one thing to understand is that as this cart accelerates to the right at some acceleration, the mass is going to accelerate down with exactly the same acceleration because they're just connected by this string. So to find the acceleration, we have to find the net force, and that would be the weight of this thing, gravity pulling down. 200 grams is the same thing as 0.2 kilograms. If you take mass times the acceleration of gravity, you can figure out the force of gravity, or what it weighs. So there's 1.96 newtons pulling down, but that force is accelerating not just this mass, but this mass as well. So that force was applied to this combination of mass. So 1.96 divided by 0.9 kilograms, the whole thing would accelerate. This would accelerate to the right at 2.18 meters per second squared, and this would accelerate down at 2.18 meters per second squared. All right, let's take it a step farther. Let's find the tension in this string. Now, tension is a force that acts through the entire string in both directions. So it's not only pulling this cart that way, it's pulling this thing up this way, everywhere along that string. So we can find the tension of it by just figuring out the force that's on this cart. So we now know the acceleration from this piece here we just did. That's the acceleration. There's only the one force acting on this mass. There might be a little bit of friction holding it back, but we're saying that's negligible. So just acceleration and mass, multiply both sides by the mass. We'll find that the tension in the string is 1.52 newtons. So there must have been 1.52 newtons pulling it to the right to accelerate that mass at this rate. That seemed easy enough, but let's now do it with this one. Let's find out how much tension. We've already found the tension. We're just going to find it a different way. So let's find out how much tension is pulling this back here. And notice that the gravity pulling down is a bigger vector than the tension pulling it up. That's going to create a net force in the down direction. So we're going to pretend we don't know that number. And I wasn't careful with my negatives here. I guess maybe I was, because this was moving to the right and the acceleration was to the right. But now I do have to be careful with my negative, because we have forces up and down. We want to make sure we're consistent. So the tension was pulling up, it's positive. Gravity was pulling down, so it's negative. You add those forces together, one up and one down, you're subtracting. That's the net force divided by the mass is equal to this acceleration, and the acceleration was down. So I multiply both sides by 0.2, and then I add 1.96 to both sides, and I do get the same answer. So that is tension goes through the string in both directions. So just how you can show that. This little device here of a mass hanging on a string over a pulley and another mass is called an Atwood machine. This is more mass than this is, so very likely, it's not surprising that this mass is going to go down and this mass is going to go up. But let's calculate how fast they will accelerate. Okay, so this is going to go down faster and faster and faster. This is going to go up faster and faster and faster. And we know the masses. I don't want to use pounds because it just gets messy with slugs and feet per second squared. So we're going to stick with the metric system here. But gravity's pulling down on this one. Gravity's pulling down on that one. So mass times gravity is its weight. And mass times gravity is this weight. It looks like both of those are in the down direction, but the pulley just changed the direction. So it's really like that's the string with no pulley. We'll say the 111 was to the left and the 200 newtons was to the right because it gets confusing with they're both moving in the down direction. So we want to calculate the acceleration. It's the sum of the forces. We're saying this 200 was positive, this 111 was negative. That's the net force, and that net force was applied to both masses. So it's the total amount of mass. And it's going to be 2.81 meters per second squared. All right, let's calculate the tension in this rope. This is a motor that's going to accelerate this thing upwards at 3 meters per second squared. And I would like to calculate what's the tension in that rope. So we still have gravity pulling down and the tension pulling up. Notice the tension pulling up was bigger than what it weighed. That way there was a net force up and it accelerated up. So this was 11.3 kilograms. Mass times gravity is its weight. So now we can say the acceleration was positive. It was up. The tension was also pulling that mass up, so it was positive, and gravity was pulling down, so that's negative. So that's the sum of the forces divided by the mass. I'm going to solve for the tension here. Multiply both sides by 11.3. I can get an answer there. Still trying to get the tension by itself. I add 111 to both sides, and then I can find the tension. And the tension is 145 newtons would accelerate that mass up at 3 meters per second squared. Another way you might see this problem is, say this rope here has a breaking strength of 2 kilonewtons, 2,000 newtons. The question now would be, how fast can you accelerate that mass up and before the rope breaks? What's the threshold here? So it's going to be the exact same situation, except this time we want to find the acceleration, and we know that threshold tension. As long as the tension was less than or equal to that, we wouldn't break the rope. And I'm not solving that for you here. I'm just showing you how to set up that problem. One last example, that this time the tension in this rope we're trying to find, but this time it's accelerating down. It's going faster and faster and faster in the down direction. Now, if this was falling in free fall and gravity was the only force, then the tension in there must have been 0. It wasn't holding it back at all. But it's lowering it down, so it is holding it up. Gravity's pulling down, there is tension up, and we want to find out what that tension is. Same thing as we had before. We find the force, what this weighs, and the net force is the tension pulling up minus gravity pulling down. Everything is exactly the same, except this time we have a -3 there. We have to be careful with positive and negative numbers. So now we're going to multiply both sides by 11.3. We're going to add 111 to both sides, and this time the tension was only 77.1 newtons. That gives you a little bit of idea how to use Newton's second law in a little bit more complicated way than you would have seen in middle school, but it has some very practical applications. That is Newton's second law.